Okay, in the last video we looked at alpha particle tracks and the helium nuclei being shot off as alpha particles there, and the fact that they were discrete lengths there, and that was good evidence that there were nuclear energy levels that were taking that missing amount of discrete energy. Okay, and we can look at that here. So what's happening there is when the nuclei are actually changed to another nucleus, in the case here of uranium being changed to thorium, it can be left in an excited state, which is normally indicated by an asterisk there, the star symbol, and the alpha particle, the helium particle, comes off, to be more exact. Okay. Now that means it's actually been raised to a higher state, this here. Now that has a range of reasons for that, but nuclear spin you could look up. There's even ones that have metastable states, similar to the electron structure ones for the atom. So when they go down to a lower state then, a lower energy state, they actually release that extra energy as a gamma ray photon. And it's a gamma ray rather than the actual normal photons we get from atomic interactions, because the forces involved are much larger. Okay, so you get a gamma ray photon, and you might get two. It does two jumps. You might get one large one, or there'll be several going on here if you go to higher levels. That communicates with a star. If it does go down to a lower level there, that could be the ground state or another lower energy level, you just draw it as non-starred when it gets to the ground state. Okay, and you get a gamma ray. Now you could indicate there's more than one ray coming off there. It's possible to get a number of them coming off if it does several jumps, so put it in there where n equals 1 or 2 or 3 and so on. Okay. Now what we're looking at today is beta minus emission. So beta minus decay will occur when you've got elements with nuclei that have got too many neutrons, say like carbon 14-6 here. This one's got 6 protons there and 8 neutrons. So 6 protons plus and 8 neutrons to balance it. Now normally it have 6 and 6, so it's got too many neutrons to be stable. So in that case what it does here is it actually splits out a negatively charged particle, electron, in this beta minus decay process. Now if you check that out, 14, this would have to be 14 because 14 plus 0 is 14. 6 needs to be the total on this side. The only way that can happen is if that's actually a 7, because 7 plus minus 1 will give you 6. So this has to be a 7. So what's happened here is carbon has changed to nitrogen in a nuclear reaction and spat out the electron in the process there in this beta minus decay process. Okay, so if you look at this in more detail, the 6 protons and the 8 neutrons have become 7 neutrons and 7 protons plus an electron being released from the nucleus. So in that case, if you look at it, we've got 1 neutron here going to a proton. 1 neutron going to a proton plus an electron. Now in that process what they found here is something different with these tracks. The alpha particle tracks were discrete, but the electron coming off in this beta minus decay process was not discrete. It came off in a range of lengths, continuous range of lengths, with a continuous range of energies then. And what they couldn't work out was where does this missing energy go, because you can't account for it with nuclear energy levels because it's continuous range. And also when they checked it, momentum wasn't being conserved. So it was proposed that there was a missing particle they did not know about, taking the energy and the momentum that was unknown to balance those there. So it was called the neutrino or the antineutrino. So let's have a look at this. A general equation can be done as X is an element with a mass number of A, atomic number Z. So the mass number does not change, the nuclear number does not change, but the charge inside the nucleus goes up by 1. You're turning a neutron into a proton. In that general equation you've got a negative electron coming out plus some energy. And to actually balance this, you should get a neutrino and antineutrino. So just to summarise that, the beta particle tracks were observed as a continuous range of lengths and therefore range of energies, continuous from 0 to a maximum. You could graph that here like that, and you've got a range of energies for the neutrino or the antineutrino. So this new particle that's proposed was supposed to have no charge, no rest mass. Now when we checked this, it's got a very, very tiny rest mass, okay? Very small one. So it's not no, but it's virtually 0, it's very close to. Now therefore it can't quite go at the speed of light because it does have a small amount of mass. So if you look at relativity, it does not go exactly at the speed of light, it goes slightly below that. So it can go up to 99.9%, I think it is, but it's not quite up to the speed of light, okay? And that carries the missing energy momentum, alright? So it's called the antineutrino when you do it with an electron. So when you do it with an electron, you've got a minus sign there. You need to remember this is the antineutrino, you put a little dash above there, okay? And it's got 0 nuclear number and 0 charge. And the energy is coming from the mass defect in this nuclear reaction, which gives you E equals mc squared as your energy production. All right. So you can do it as a general equation, or you can do it as just showing a neutron going to a proton plus an electron within this nucleus. Okay, now if you check what's happening here, is we're going to go down by 1 neutron in this reaction here, and up by 1 proton. All right. So going back to your neutron-proton ratio graph, if you check that out then, the result will be it will actually move the parent nucleus to a daughter nucleus which is in that direction. So checking that out, anything above this line of stability then has too many neutrons, this section of yellow here. And in that case, with having too many neutrons and converting it down to a proton, it's going to move in this direction. And so it should take radioactive nuclei and get them towards that line of stability. Now in the case of these heavy elements, don't forget, they're going to release a helium nucleus in the alpha particle decay, which is basically 2 protons plus 2 neutrons. And in that case, you're going to get the parent nucleus going down by 2 neutrons and going down by 2 protons because it spits them out. So it's going to head that down and produce a daughter nucleus closer towards the line of stability. So off the end there we've got alpha decays that process, beta minus decays in this part of the process. So the next thing to look at is the beta plus decay, which is below the line there. Now the process of beta plus decay occurs for those that have too many protons, which is different. So this particular fluorine has too many protons. So what we're going to do here is going to convert a proton into a neutron, the opposite to what we did in beta minus decay. So this is going to release what's called a positron, which is identical to an electron there, except for it's got the positive charge instead of the negative. This is what we refer to as an example of antimatter. It's an anti-electron, okay? Now in this process, if you check it, this is going to produce an 8 there, because 9 is equal to 8 plus 1, and you've still got a mass number of 18. So you've still got the same number of nucleons, but we're going to cause the protons to go down by 1, and therefore the neutrons to go up by 1. So if you look at that there, a proton is turned into a neutron, plus a positron being released from the nucleus. And to balance this out, just as in the beta minus decay, we need to conserve the momentum and energy. We need a neutrino this time rather than an anti-neutrino. So this is a neutrino coming off, which takes the missing energy and momentum, and that's why you can get any continuous length there. Don't forget, it's also possible that this daughter nucleus could also be in an excited state and decay and release a gamma ray, by the way. It's just that it's hard to pick that out when you've got so many tracks going on of different lengths. You won't know if this one suddenly appears to only be this length instead of the length it was at. It's just too hard to distinguish it there. Okay. So what's going to happen in the general equation is you're going to get that staying the same. This time the atomic number goes down by 1 when it releases a positron. So this is your antimatter. No negative there, no dash needed. Okay. So what's going to happen here then is the proton number is going to go down by 1 on that graph, and the neutron number is going to go up by 1. So in this case, it's going to move this way on the neutron to proton ratio graph, where it shows you stability. So that's going to occur for those elements below the line of stability. It's going to convert that from a proton to a neutron. And that's not naturally occurring. Those positron emitters doesn't occur naturally, so we normally have to make them in a cyclotron to get that increased number of protons inside the nucleus and make it unstable. So that's the sort of thing that goes on for a PET scanner, which we're going to look at later on. Okay, let's have a look at that. So in this one here, the beta plus ones are below the line there because they've got too many protons. They're going to remove the proton there, gain a neutron in that process there, and move in that direction to a daughter nucleus which is closer to the line of stability or even on it. Okay, thank you.